Hello everyone, and welcome to this final video dealing with for BC Calculus and dealing with vector valued functions. In this case we are going to be doing a number of different things. This combines three sections of the book into one video, so it could take a little bit longer, but first thing we're going to do is define a vector valued function. What exactly is it? Number two, extend the concept of limit and continuity to vector valued functions. Number three, differentiate vector valued functions. 4, integrate vector valued functions. Number 5, describe velocity and acceleration associated with vector valued functions. And number 6, use vector valued functions to analyze projectile motion. First, let's go through and define what it means to be a vector valued function. And the way it works is this: any function in the form where vector r of t is equal to f of t times vector I, remember I is the vector 1, 0, plus g of t times vector j, which is a vector 0, 1. This is what's called a vector valued function, where the component functions f and g are real valued functions of a parameter t. And another way of looking at it is this: r of t equals the vector f of t g of t. Now, one other change that can happen on this, in terms of AP notation would use ordered pair notation. So they would look at this, the vector r of t, as f of t, g of t. They would use that ordered pair notation. So just be aware of that as you're working on these things, and when we start taking a look at review materials, that will be how a lot of these vector valued functions will be notated. Now let's look at a couple of examples. The first one, r of t equals is the vector valued function 5 minus t times vector I plus the square root of t times vector j, which the other way of notating that would be equal to the vector 5 minus t square root t. And number 2, r of theta, the vector valued function r of theta, is equal to 3 cosine of theta times I plus sine of theta times j. So in that particular one, that vector valued function would be equal to the vector 3 cosine theta, then sine theta. I use the AP notation there. Now, another thing that comes into play here and we talk about is this idea of what it means to be a limit, and also what it means to be what continuity means here. So we're just going to kind of extend that. And really, the limit aspect and continuity is really not much different than what you would expect. In terms of these things, like if I work with that first one, so I want to take the limit as t approaches 3 of r of t, which equals the limit then as t approaches 3 of our vector 5 minus t and square root t. That is going to end up being what happens when I just plug in t. So I'll get 2 square root 3. That would be the limit of that. Now, what does it mean to be continuous? Well, remember, the continuity means that that limit exists. Remember, with continuity, we had three parts. The limit had to exist. The function value had to exist, and the limit was equal to the function value. And so we were able to combine that into one statement, and that can also be combined in this case too when I'm looking at continuity. When I'm looking at continuity, I can go through and I can say we know it's continuous. This vector valued function is going to be continuous at some value t equals a if the limit as t approaches a of that vector valued function is the same as r of a. If this is true, keep in mind that means the limit exists, the function's value, in this case, the limit exists here, the function's value exists there, and the limit is equal to the function value. Therefore, this vector valued function is now going to be continuous at t equals a. Now let's go and sketch this plane curve that's defined by our vector valued function 5 minus t and square root t. Now you're going to look at this and say, wait a second, this looks very familiar to what we did with parametrics. And you would be right. It would be very similar. It would be the same. So when we work with this, I'm going to plug in. The first thing I'll do is I'm going to plug in these values for t. Now I picked these values for t mainly because of this part right here where we had a square root. I wanted to use ones that had perfect squares or perfect square roots for t to go through and make my life a little bit easier. So when I plug in 0 into the first part, I will get 5. When I plug in 1, I'll get 4. When I plug in 4, I'll get 1. When I plug in 9, I'll get negative 4. When I plug in 16, I get negative 11. And when I put 25 in, I get negative 20. And then when I work with the square root of t, when I plug in 0, I'll get 0. When I plug in 1, I get 1. When I plug in 4, I get 2. Then 3, 16 gives me 4, and 25 gives me 5. Now you'll notice I did make a change onto the grid. When I made the grid, I forgot to go and put in the portions over to the right. So now let's go and sketch this plane curve. So for this curve, I am going to go through. I know I have my first component is a horizontal, second component is vertical. So my horizontal component is 5, my vertical component is 0. So that's going to put me at the point 5, 0, which is right there. So at t equals 0, that's where I'm going to be. At t equals 1, I'll be at the point 4, 1. So that's going to be t equals 1. There's t equals 0. At t equals 4, I'll be at the point 1, 2. So there's t equals 4. At t equals 9, I'll be at the point negative 4, 3. So negative 4, 3 there, about right there. At t equals 9 or 16, I'll be at negative 11, 4. So I'll be right around here. 16. And t equals 20, I'll be out here. I'll be at negative 25. So I'll be right around there. So my path of my object is here. This is my curve. Now remember, anytime you're dealing with a plane curve, the orientation must also be put into place. Okay, so what I have here is really I am traveling with a vector. So what I have when I'm looking at this is my plane curve. I know I'm going to be taking motion. My motion is going to be along here. But at each one of these locations, because it's a vector valued function, I am going to actually go through, and when I'm calculating these different pieces, I am calculating a vector. That's going to go from the origin to each individual point. So I'll have a vector that will go there, like that. So it'll come up like this. And that would be the vector that got us to t equals 9. But this again is the motion that I'm actually going through and looking at. Now let's take a look at what it means, how we go through and find the derivative of a vector valued function. So in this case, we're going to let f of t and g of t be differentiable functions of t, such that the vector valued function r of t is f of t times vector I plus g of t times vector j, or I can say it f of t comma g of t with the vector notation there. Then the derivative of the vector valued function r of t with respect to t is going to be the vector valued r prime of t is f prime of t times I plus g prime of t times j, or basically written as a vector, the horizontal component is f prime of t, the vertical component is g prime of t. This same idea exists for our second derivative. In this case, the second derivative is just going to be f double prime of t, g double prime of t. Now you'll notice on this that this is different than what we did with parametrics. As you're looking at these, I'm expecting that you do see the similarities between the vector valued functions and parametric equations. But we have a difference here. Remember when we took the derivative of a parametric, we took the derivative with respect to t of dy dx before, and we still had to multiply it by the derivative of x with respect to t. In this case, we're not doing that because we are working as a derivative with respect to t, whereas with the parametric equations, we were working with a derivative with respect to x. So notice the difference, and that's why you're not going to see, we don't have any real crazy tricks or anything that we have to worry about in terms of identifying that the second derivative. We just take the second derivative of the horizontal component, second derivative of the vertical component. Now let's take a look at a couple examples. We're just going to take the derivative of these vector valued functions. So in this case, r prime of t is going to be 2 times the derivative of cosine t, so that's going to end up being negative 2 sine t. And then the vertical component will be the 5 times the derivative of sine t, so I'll get 5 cosine t. Now on this next one, r of t in this case is t squared cosine t. So you'll notice we do have a product rule that we have to take into account, and the vertical component is negative square root of t. So in this case, I'm going to start out by thinking of this as t squared cosine t, and then negative t to the 1/2 power. So when I take the derivative of this, r prime of t, now I have to use the product rule in the for the horizontal component. So that's going to be 2t cosine t plus t squared times negative sine t. And then the derivative of the vertical component is going to be negative 1/2 t to the negative 1/2 power. Or I could go through and say it's 2t cosine t minus t squared sine t, and then negative 1 over 2 square root of t. However I want to do it, I could leave it as exponential notation or put it in terms of the fraction. I don't even have to actually simplify the horizontal component either. And then the last one we have, r of t. These actually should be vectors in each case. R of t on this last one is the vector e to the negative 2t, arctan t. So r, the derivative of that vector valued function r of t, is going to be the derivative there is going to be negative 2 e to the negative 2t. And derivative of arctan is going to be 1 over 1 plus t squared. And that would be our first derivative. And I could go through, if I wanted to, I could take the second derivative, just taking the derivative of each one of those components. Now, throughout the year, we've talked a lot about, whenever we've talked about a different function, I've always mentioned that we would look at this thing and say it's a nice smooth curve. So because that smoothness meant that we would have a derivative that we could calculate. Okay, if we had a cusp where it wasn't smooth, we had a sharp point, sharp change in direction, obviously then the derivative doesn't exist. And so what we have to do with this, we also need to have an idea what it means in terms of vector valued functions. What does it mean to be smooth? Okay, so what we're going to do is we're going to let r of t be our vector valued function, and it's going to be f of t of g of t. Now this vector valued function r of t is smooth on an interval I when f prime of g and g prime of t are continuous on I. Okay, so on that whole interval, f prime, for every value of t in that interval, f prime of t exists and g prime of t exists. There's a value that comes out. Okay, and here's the key part. The vector valued function at t does not equal 0 for any value of t in that interval. So what this means, and this is the 0 vector. So in this case, when we take this, when we plug in a value for t, we don't get the vector 0, 0. Okay? If we get, as long as we get anything other than the vector 0, 0, when I plug in t, we know it's smooth on that. Now here's an example, and this one comes from the book. It is on page 826 in the book. You can see the graph of it, of that plane curve there. But r of t in this case is equal to 5 cosine t minus cosine of 5t, and then 5 sine t minus sine of 5t. So if I take the derivative, r prime of t, I get negative 5 sine t plus 5 sine 5t, and 5 cosine t minus 5 cosine 5t. Okay, so now what happens on this? Okay, I look at this, I can look at these two pieces individually. They are sum or differences of sine functions. And so sine functions are continuous over the entire real number line. So therefore this is defined. It is continuous on that whole real number line. And same with the cosine function here. It's continuous over that. But if we take something like, we pick a value, and I'm going to pick r prime of 0 is going to be negative 5 sine of 0 plus 5 sine of 5 times 0, which is going to be 0, and 5 cosine 0 minus 5 cosine of 5 times 0, which is also 0. And what I get then is sine of 0 is 0, so that's going to be 0 plus 0, and this the other portion, cosine of 0 is 1, so that's going to be 5 minus 5. And so what I get when I do that is the vector 0, 0. So in this case, when t equals 0, I get the 0 vector, and therefore I know my function, my vector valued function, the graph of it is not going to be smooth at t equals 0. I'm going to get, when I do that, I'm going to get a cusp. So when I plug 0 in for t into the original one, I'm going to generate a point, and I know that point is going to be a cusp. Now let's take a look at the integration of vector valued functions. So this one right here, it's going to feel, I think it will seem pretty straightforward, and I think it will make sense to you. In terms of this, if r of t, the vector valued function of r of t is f of t times the vector I plus g of t times the vector j, where f and g again are continuous on the interval from a and b, then an antiderivative of r prime of r of t is the integral of the vector valued function r of t dt is going to be the integral of f of t dt times vector I plus the integral of g of t dt times vector j. And if I deal with the definite integral, it's just going to be the definite integral of each piece to give us that vector valued function, the integral of that vector valued function. Again, let's take a look at a couple examples now. In this first case here, I have the integral of secant squared t times vector I plus 1 over 1 plus t squared times vector j dt. So I know that this is just going to equal the integral of secant squared t dt, that integral times I, plus the integral of 1 over 1 plus t squared dt times vector j. And so in this case, now the integral that I have here, the integral of, and keep in mind this is an indefinite integral, so that's the integral of secant squared t, that is going to equal, it's going to end up equaling the tangent of t plus some constant times vector I plus, this is going to end up being the arctan of t plus, we'll call that first constant C1 plus the second constant C2 times vector j. And then the result then is going to be, this is going to be the tangent of t times vector I plus the arctan of t times vector j plus some constant vector. Now, sometimes they could give you some information which would allow you to calculate like they could tell you the initial horizontal position, the initial vertical position is going to be these values, and then you could use that to go and calculate C1 and C2. So you wouldn't necessarily have to have that constant vector, but in general, that's what you have. Now, if I want to take the definite integral here, I know this is going to end up equaling the definite integral 0 to 1 of 8t dt times I minus the definite integral from 0 to 1 of the coefficient on j is 1 dt times j, which the antiderivative 8t, now we do that, that's going to be 4t squared. So that is going to be 4t squared going from 0 to 1 times vector I minus the antiderivative 1 dt is going to be t going from 0 to 1 times vector j. And so when I calculate that, that is going to end up being 4. When I plug in 1, I get 4 minus 0 times I minus 1 minus 0 times j. So I get the vector 4I minus j, or the vector 4, negative 1. That would be the antiderivative of the definite integral of that vector valued function. All right, now that we've done all this stuff with the vector valued functions, you've dealt with parametrics, now we're going to start looking at this in terms of think of that in terms of velocity and acceleration, actually looking at motion. So in this case, x and y are going to be twice differentiable functions of t, and the vector r is going to be a vector valued function given by the vector r of t equals x of t times vector I plus y of t times vector j. Okay, typical notation. So our velocity vector v, the velocity vector v of t is going to be x prime of t times vector I plus y prime of t times vector j. Or if I wanted to, I could sit there and say that's the same thing as x prime of t and y prime of t. And our acceleration vector is x double prime of t times I plus y double prime of t times j. Or again, as if I want to, in terms of our notation, I could say that is equal to x double prime of t, y double prime of t. Okay. Either notation is fine, whichever one you're comfortable with. Again, remember, I'm still using the less than greater than signs for the vectors, but the AP will use parentheses on that. And the last thing we have is speed. Well, we remember speed is the magnitude of our velocity vector, and so in this case, the magnitude of our velocity vector is going to be the square root of x prime of t, that thing squared, plus y prime of t, that thing squared. So now let's take a look at a problem here where we're going to have to go through and we want to find, in this case, we want to find the velocity vector and acceleration vector and speed for our vector valued function. R is r of t equal to the vector t squared and 2t to the 3/2 power. And we want to do this L at t equals 4. Well, the first thing I have to do is take the first and second derivatives. So to find the velocity vector is just going to be the derivative of each of these. Well, the derivative t squared is 2t, and the derivative 2t to the 3/2 power, I bring the 3/2 down, so I get 3t to the 1/2 power. And then the next derivative is going to be the acceleration vector. The acceleration vector is the derivative of our velocity vector, so derivative 2t is 2. And now the derivative of 3t to the 1/2 power is going to be 3 over 2 t to the negative 1/2 power. And now what we want to do on this one, they do want to know what is our velocity and acceleration vector and speed at t equals 4. So our velocity vector at t equals 4 is going to be what happens when I plug 4 in for t. So I'll get 2 times 4, and then 3 times 4 to the 1/2 power. And so I'll get the vector 8 and then 6. Our acceleration vector, in this case, a of t, our acceleration vector at t equals 4 is going to be 2 and 3 over 2 times 4 to the negative 1/2 power. And so in that case, I'm going to get 2, and 4 to the negative 1/2 power is 1/2, so I get 2 and 3/4. So there's my acceleration vector. The only other thing they want us to do is the speed. Well, in this case, our speed is going to be the magnitude of our velocity vector. So if I worked with the vector, I'm working at t equals 4, I know that the velocity, the magnitude of that, v of 4, is going to be the square root of 8 squared plus 6 squared, which, if you remember from your Pythagorean triples, that's going to be 10. So that would be the speed of this object, whatever the units are, though. And finally, we get to projectile motion. Now, in this case, we work in fantasy land a little bit, and that we're going to ignore air resistance because it would always come into play in terms of just the friction associated with traveling through air, as well as any type of wind that would be blowing in whichever direction that would cause a change as well. So we're just going to work with it in terms of, we're going to ignore all that, and we're just going to look at that. Look at the projectile motion based on just our angle and our velocity and the height that we have. So we're going to ignore air resistance. The path of a projectile launched from an initial height h with an initial speed v0 and an angle of elevation theta is described by the vector valued function r of t equals initial velocity times the cosine of our angle of elevation times t times vector I plus, and now it's a big group, our h, which that's our initial height, h, plus v0, our initial velocity, times the sine of our angle of elevation, minus 1/2 gt squared. G in this case is the acceleration due to gravity. Now, a lot of times when we dealt with this before, we would talk about it in terms of, since gravity was pulling down, it would be a negative. But because we're working in this, it's a minus right there. We will use just positive values for G in this one. If that was a plus, then we would have to use a negative value for G. So it's minus 1/2 gt squared times vector J. And when you're working on these ones, if you're working in terms of feet, you're going to use G as 32 feet per second squared. And if you are working with meters, you'll use 9.8 meters per second squared. Okay, so just be aware of those, and you just you plug those in, and that will get you the vector valued function for that, and then you can do whatever you need to in terms of the analysis of that projectile motion. So I know this was quick. There's a lot of stuff here, but this does conclude all new material for the AP exam. You should be working, completing the assignments. I will today. I will go and post a review assignment for you to work on that you'll then submit to me through Classroom. I will probably post that Thursday or Friday. So with that, I hope everything's going well. If you have questions, do not hesitate to ask me on Remind or Classroom. If you would like to talk to me, let me know, and I will set up and we can set up something on Google Meet or on Zoom or some way that we can sit and talk and see each other face to face. So with that, I hope everything's going well, and I hope to hear from you soon.